Okay, no need to follow along with this part. I'm going to create a Jupyter notebook and I'm just going to visually display and explain a few things. Okay, so first I need to install Jupyter. And then run my Jupyter notebook. I'm not sure if you've ever seen one of these before, but it's really simple. And it'll open up a browser and it will give you something like this. And I'm going to create a new notebook in the root of my project. And you'll be able to go and look at this notebook in the repo that I create at the end. Okay, so we've loaded up our Gettysburg file and we've just got 10 seconds at this sample rate. So we've got this number times 10 individual samples. And we're going to plot our audio wave first. Might have an error, I might have to roll back my version of matplotlib. I had some problems with it before. Yeah, okay. So what I'm gonna have to do is I'm gonna have to, this is not important. This is just, okay. Fix that. I had a, and the version of matplotlib that I had, I just had to roll it back by one. There was some issue with it. Anyway, now we can see our audio wave. And so this is what the data actually looks like. It's the first 10 seconds, as you can see down here. Okay, so this is our audio wave. We want to turn this into an audio spectrogram. Now, librosa provides us a really easy way of doing that. There we go. So this is an audio spectrogram. So what we can see here is, so this is our wave, and you can kind of see how this loosely corresponds. So you've got a big, like lots of activity down here, and then a big streak, lots of activity down here, sort of some big streaks, and they sort of roughly correspond to big streaks here. Now, what this image represents is, it's a three-dimensional plot. We're going to change the color of it because it's not very easy to see. And Verno, this is my favorite color scheme, and it's the one we're going to use later. So this is a three-dimensional plot. Basically, we have the time axis along the bottom, we have the frequency axis along the top, and where we have this X and Y meeting, the intensity of the pixel represents the frequencies present at that time point. So, as we go up at this time point, exactly 1.5 seconds, the intensity of the pixel at each frequency height represents the presence of those frequencies at that time point. And so the actual color, this represents decibels. And so you got, down here, negative 50 decibels, that's really quiet. And then 20 decibels, that's, that's moderately loud. Like you can hear that. And so this is something that's generated for us by librosa, and it's great. But the problem is we want to make a live spectrogram. We want this to scroll past continuously. We don't want to take We don't want to load in a file and load it all up at once. We don't, that's not what we want. We need to figure out a way to take this, what this does, or this exact functionality, and we need to replicate it so that we can compute a single strip at a time. And then the next time point, we'll compute another strip. And the next point, another strip. And so we can have it scrolling along the screen at a frame rate that we specifically want and we can choose. And we just want to be able to feed a small window. Remember, we've got our windows. We want to feed one of these windows and then have it compute a slice of our spectrogram. So that's why I showed this before, because we're going to be using these overlapping windows, and you don't want to, you know, we definitely want some overlap. This is just the part of the way that this is calculated. And LibRosa is doing a lot of this stuff internally as well. That's why I sort of introduced that sort of, you know, scroll, like sliding window concept. So what I'm going to do is I'm going to type out everything we need to replicate this exact functionality, but in a way that's going to allow us to do it slice by slice by slice. We're going to create a few functions in here, and we're going to reproduce exactly this in our different method. We're going to create an image that produces exactly this spectrogram. So we're going to create that image, and then the functions that we create to do that, we're going to copy paste them into our project. And so we're going to have everything we need from there. But I just thought it would be important to show what we're doing, how we got to this. So if you want to go and look up LibRosa, this short-term Fourier transform, what does that do? How does that work? You know, you can, you know, I thought it was important to show you where this came from. You know, I didn't just pull it out of me. Okay, one of the first things we need is something called a Hahn window. And NumPy creates one for us. Oh, sorry, not a Hahn, a Hanning window. I just call it Hahn just for short. And what does this look like, you ask? It's this particular shape. And you can look this up further. You just go to Wikipedia, Hahn function. So it's this function that is used to essentially, I'll show you in a second. But if you want to look up this a little bit more, you can come there. Now, what we want to do is we want to I'll grab a section, I'll grab a window of our data. So that's the first thing I'll do. So I'll grab, say, the 20th window. So the way that we do that is grab that slice. So from the from our window size multiplied by 20 to window size multiplied by 21. So we're going to grab essentially the 20th window size. I'm sure you can see how that gives us what we want. I'm going to plot that. So this is just a small section of our audio wave, one window's worth. And you can see, you know, the sort of repetitive, you know, pattern. This is only about 1/20th, roughly, about 1/20th of a second, because it's 1024 samples long, and we have a sample rate of 22,050 samples per second. So this is about 1/20th of a second, roughly speaking. Now, what we want to do with our window is we want to turn this signal into a sort of wavelet. We want to multiply these two, and I'll change this. Give me 1 second. Change that color there. So we want to multiply these two lists that are the same length, 1024. We want to multiply this one by this one, and I'll show you what that result gives us. So we want to taper our signal. So we want, basically at the edges, we want to lessen this, the edges, and we want our signal to be concentrated in the middle. And this is necessary because of the way that the discrete Fourier transform, or the fast Fourier transform works. The fast Fourier transform will give us, actually, let's have a look. So sure we can find an image that shows us Found a good one the other day. Okay, here's a good one. So what we have here is our signal image. What we have along here is our signal. Now what we want, so this is the sort of the time domain. You can think of it as that. So as it goes tick 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 tick, it's moving along in time. Now, but what we want, we have our signal in this form. We want our signal in this form, which is the signal, the frequency domain. Sorry. We want to know, see, we've got a signal here, so it's a spike, and then another signal here, it's a little bit not as strong, so it's a little bit less, a little bit less, a little bit less. So the Fourier transform allows us, actually this is a much better one. The Fourier transform allows us to go from the time domain into the frequency domain. It also allows us to go in the reverse direction, potentially as well. So it allows us to do lots of fancy things with signal processing, but what we are interested in is going from the time domain to the frequency domain. So we want to take our small section of a signal and we want to figure out all the frequencies in that tiny little signal. Now, we can't just give our entire file and figure out what frequencies are in it, because we won't be able to tell at time t what frequencies, time t plus 1 what frequencies. It's just going to be one jumbled mess. So that's why we need a tapered section, a tapered window, and then we feed just that tiny little window and figure out what frequencies are just in that little slice. That's why we're sort of going through this annoying process. And I hope that I am explaining it somewhat. You're not going to be an expert in this. I'm certainly not an expert. But you should have enough to understand at least roughly what's going on. So I'm going to plot our tapered signal, and I'm going to plot our Hahn window on top. So we'll see what that gives us. And let me just fix that. Okay, so see, this was our signal, right? Where the edges, it's really pumping. But what we've done is we've created a sort of wavelet. We have tapered off the edges so that the frequencies are really pumping. We care about the frequencies more so in the center than on the edges. We want to sort of quieten those down so that we can just see what's going on in this little packet. So that's why we do that. And that's like just the setup. That's what this little Hahn window does. We'll see sort of how that fits together. So sometimes our window might not be the full 1024 or the window size length. In that case, we're going to pad the rest of it with zeros so that we're always going to have a window that is of the right size, but we'll be able to pass it a size that is less than that. And then if it's the full length, then we can just continue on. We just need to taper our window and then perform the fast Fourier transform on that, which is going to pluck out our frequencies from our short little wavelet. And NumPy contains all these functions for us. We don't have to write them ourselves, and we probably shouldn't, even if we wanted to. We can, if you guys would like to see that. I reckon that would make a really fun video. But NumPy and other packages, they have like really, really fast, really, really efficient implementations of this. So, there's no need for us to write it ourselves unless we're doing it for like educational, fun purposes, which does sound like fun. So we're going to be able to clip or specify the minimum and the maximum decibels for our signal, because see the sort of range of colors or the range of decibels, we might want to clip you know, we might want to just throw away anything that's too loud, and anything that's like below a certain level, we might just want to throw that away, so that we can, you know, have a consistent sort of tone for our spectrogram. So that's why I've included these. And that one was -50. I think max dB was 30. So we just set those as default. So our slice, we need to get the absolute value, the magnitude, and then, or the amplitude, and then we can convert that to decibels with libRosa does that for us. Remember this slice, this is going to be, it's going to get this for us. So we're going to grab a slice and we're going to feed it straight to our color. And we want to scale the full range, so the minimum to the maximum, we want that between 0 and 1. So we shift whatever the min is, could be positive, could be negative, we shift that to the 0, and then we divide by whatever the total range is, so the maximum minus the min, and that'll give us a range between 0 and 1. And it's going to be important for the next step, so that we can pass it to our color map. That we brought in before. It requires, or it's going to need something between 0 and 1. And once we get that, we're going to convert it to RGB pixels. And it's really easy to do. We'll multiply it by 255 so that we have, you know, 8-bit pixel values. And this should give us an RGBA image, but we only want the RGB. So we're just going to slice that. We'll return our slice. Now we are going to take this, our XDB, whatever that is, we're going to make an empty two-dimensional array of exactly the same, or roughly the same size, but with a pixel channel. So we're going to loop over all of our slice. We're going to loop over our entire width of our image. So we're going to go all like this entire way, like this entire direction. So we loop over the width, and we're going to compute our slices. And we update that slice. And should be it. And then we check out the shape of our Y, which is our image, and we can display our image. We're just going to need to use the package pillow, which we should already have installed. And then we can just go image.fromArray, which is what our Y is. And there we go. Now it's upside down. So it's this. What we'll do is we'll grab this and we'll display it. Now I'll change this size. We'll display it right underneath. Change this, make this a bit bigger. So there we go. Looks very, very similar. What we'll do, we'll reverse this. That should do it. There we go. Okay. So now, if you look really closely at these two, they are practically identical. Like, they are absolutely bang on. Like, they're almost exactly the same. And I mean, I seriously doubt you'll be able to see any like visual differences between them. And so the whole point, so this is the one that was generated by libRosa. and this is ours. This is our image. Now the beauty of this is we can compute it slice by slice using these functions. So that is the whole point of like why we've done this, and this is how we got there, right? This is all the different steps, what's involved, all that kind of stuff. Now we've got what we need. So we can take these functions, these two, slice, or we can combine them into one function. That's fine. I don't really see. There's not really any need to separate them. When I came up with it initially, I tried out lots of things. That's how I ended up with. But we could combine them. Yeah, 100%. That would be cool. And we're going to take these and we're going to stick them in our new spectrogram file, just like we created for the wave. We're going to create one for a spectrogram, and we're going to include these functions, and they're going to generate everything for us. So when we add a window, it's going to compute everything for us, and then it'll be really, really sweet. So again, you didn't have to code along with this. I just felt like it was important to show where I got this from, how I came up with it, all this kind of stuff, and some background on what's going on under the hood in case you are interested. So now we're going to get back to coding, and we're going to get back to our spectrogram, and we're just going to smash out the rest of it. It's going to be super fun. Let's go.